Hi, and welcome back to another episode with It's Dr. Dan, and this time we're going to be looking into gas laws. So last time on our previous video of Introduction to Gases and Kinetic Molecular Theory, we learned that we have little gas or little particles that are bouncing all over the place, moving in constant motion, and they're applying pressures with inside of whatever space they are located in. They fill whatever volume they are currently in. So for example, the air in your room, it's in every square inch of your room. It's not just in one little location around our mouth, it is everywhere. And that's because all those millions and millions of atoms that are all around are all bouncing around and moving and flowing. So there are a lot of very simple laws, being that these are ideal gases, talking about very minimal interactions between each other. We can describe them with laws, meaning that we can use a lot of mathematics to describe how can we predict how they're going to function. So one of the first ones is Boyles Law. So what Boyles Law tells us is that whenever you have a pressure and a volume of a gas that are initial, so whenever we have something that's considered to be initial, we're going to be representing that with, so if I have an initial pressure, that's going to be with a 1. If it's an initial volume, that would be V1. So whenever you have those two values, they are going to be equal to a final pressure and a final volume of that gas. Meaning that, let's say if I took a balloon and I'm holding it in my hand, well, what were to happen if you were to try to compress it in your hand? Is it going to resist you or is it going to pop? Well, if while you're pressing on that balloon, you're going to feel it resisting you until eventually it pops. But for the longest time, it will resist. That's pressure. So the whole idea of that is that there's this inverse relationship here, meaning that as you increase pressure, the volume of which that gas is occupying is going to decrease as a result. So we can make a lot of predictions here. So as pressure increases, going from P1 to P2, volume is going to decrease. If you go from P1 to P2, so initial to final, and it's decreasing, the volume is going to be increasing as a result. So what does that look like in terms of graphing? Well, if you have, let's say, looking at this, if we have our initial pressure at initial volume, and let's say I decrease the pressure and I go down. So if I'm going downwards, well, as that goes down, well, what's happening is, well, the volume is going to be increasing. So volume goes up as pressure goes down. So it's all about that inverse relationship. So how can what exactly are you going to have to solve mathematically? Well, it's generally pretty easy questions. So if I have the following one and I ask you this question here, and I say that we have a sample of gas and it's placed inside of a piston. Well, a piston essentially is this metal cylinder. It's going to be pushing down and it's going to be compressing all the gases like I have here. So if I have a little piston here, I have a gas inside of here. They're bouncing all around. And this occupies 425 milliliters at 1 atmosphere. So let's try to highlight all that important information. So we have 525 milliliters, and that's at 1 atmosphere. So whenever you're reading these, what we want to do is we want to write down all of our given pieces of information. So we have 425 milliliters, and that's at 1 atmosphere. So that tells you your V1 and then your P1 of those two values. Now it mentions that the gas piston is compressed. So you can see that, it's coming really close together. So it's like the example I said, if I push on a balloon, what's going to be happening? So when that compresses, it says that the pressure reaches 3.28 atmospheres. So that means that as this pressure is changing, it goes from 3.28 atmospheres. So what you see is that pressure is increasing. So how can we try to predict this problem? Well, going back up, well, as pressure increases, so looking at these, right? So pressure increases, volume should decrease. So it's telling you that your final answer should be a tinier volume. It's a check for yourself, which makes really nice for when you're doing these problems. We like predictable problems. We don't want something that it goes into something that doesn't fit anywhere. So we're trying to figure out V2. So what we're going to be doing initially is setting up our formula, meaning that I have P1 V1 is equal to P2 V2. So we are trying to solve for V2 here. So V2 is our unknown variable. So the whole idea here is we need to get it by itself. Well, what's the easiest way to do that? Well, if I divide both sides by P2, what that's going to cause is for the P2 values to cancel, and that will, in a sense, get V1 by itself. So we have P1 times V1 divided by P2, and that's going to be equal to V2. So all we now need to do is plug in all of our information. Now, when you're plugging these things in, whatever the common variable is, so in this case pressure, they need to be in the same units. They need to be able to cancel each other out. So when we are doing this, right, our initial pressure was 1 atmosphere, and that's going to be multiplied by 425 milliliters, and that's all going to be divided by pressure 2, which is 3.28 atmospheres. All right, so when we do that, what that's going to be all equal to is that V2 will be equal to 129.6 milliliters. Now, is that the correct sig figs? We always going to round it, and you might notice there's 3 sig figs for all of your givens. So this will round to 130 milliliters. Okay, and now this will be your final answer there. So that's how we do Boyle's Law. Now, for the next one, Charles' Law. Charles' Law is another type of another really common gas law. So what this is telling you is that volume is directly proportional to temperature. And this could kind of make some sense if you think back to the simulation I showed in my previous problem, where as we increase temperature, particles start to move at a very rapid pace. So when that happens, those particles are going to be pushing and banging against all the walls of whatever its container is. So if it's something that's flexible, well, it's going to grow as a result. So they're proportional. So meaning that if as initial volume, if that's going to be increasing, then you're going to see a proportional change in your final temperature and final volume. So the way that we can look at this is a very different graphical picture, is that if I have volume at an initial temperature, and if I increase the volume, temperature is going to increase too. They're both going to increase. So if temperature increase, volume should increase too. They are directly proportional. Now, one of the things about this is, being that we're talking about temperature, this is one of the units that needs to be in the correct scale. It needs to be in Kelvin. Now, the reason behind that is because this Kelvin is an absolute unit scale, meaning that it only refers to positive values. You cannot do the mathematics here with negatives or with 0 as a possibility. It has to be a positive number. So anywhere from 0.0001 all the way to infinity, right? So it's always a positive value. So now this is also predictable. As volume increases, temperature should increase. If volume decreases, temperature should decrease. So we should be able to predict our answer too, which is always a nice thing to have. We want as predictable as possible. So the idea with this one, if I have the following question. So if I say I have a 2.75 liter sample, okay, so we have a volume, and it's at a temperature at 25 degrees C, when the amount of gas and pressure are held constant, so being that's telling you that it's not relevant to this problem, it's helping you be able to decide which formula to use. This time we know it's Charles' Law, but most problems you're given, you have to pick from all of them. What is the new volume when argon is heated to 45 degrees C? So argon is being heated. This volume of gas is going to be growing because they're moving more rapidly. So Now keep note, we do have to convert all these to Kelvin. So we have to use our little Kelvin equation. So why don't we write down all these values we had. So we had that volume 1 was 2.75 liters. We don't have a volume 2. Kind of going through these. So we have no volume 2. That's a question mark. And T1 and T2 were 25 degrees C and 45 degrees C. All right, so when you're going through these, the first thing we have to do is convert our temperatures to Kelvin. So in order to do that, we just take our temperature. So if I have T1, Kelvin, this is going to be that 25.0 degrees C plus 273. And what that's going to give us, our first value is 298 Kelvin for T1. And then T2, doing the same mathematics, you're going to see that that one's going to be 318 Kelvin. All right, so now we can plug it into our equation. Our equation before was V1 T1 is equal to V2 over T2. So what we're going to do is we're going to rearrange it to get V2 by itself. So what we can simply do is, being that we want to get this by itself, we can multiply both sides by T2. This is going to cause the number of the T2s on the right-hand side to cancel, giving us a new formula, or a rearranged formula, of this is equal to V2. And what we're simply going to be doing is plugging in our variables. So we have T2, which was equal to 318 Kelvin. We have V1, which was 2.75 liters. And then we have T1, which was 298 Kelvin. Now, notice how the Kelvin ends up canceling each other out, leaving us only with a volume. So when we go through this calculation, what we're going to end up getting is 2.93 liters of gas. Now, does that make sense based on what we saw? Well, as you notice, temperature was increasing as we went from T1 to T2. So if that's the case, volume should also increase. And based on our original volume, you can see that increased by a little tiny bit when it was heated up. So this gives you an idea of what we are looking for with this gas law. So as volume increases, temperature should also increase. Same thing with vice versa. As temperature decreases, volume should decrease. The next law, so there's a lot of these, but we'll go through them step by step. This one is Gay-Lussac's law. This one's also a very similar idea. This one tells you that as pressure is directly proportional to temperature. So if you think of your car tires, for example, throughout the summer, as it gets really hot out, the pressure of your tires is going to increase. This is one of the reasons why your tires have a maximum recommended pressure on your tires, because if you overfill them and then it gets hot out, they will explode. Versus when it gets to winter time and you might have that air pressure light that comes on saying low pressure. Well, it's because all those molecules are getting really cold and they're starting to kind of trying to bundle up really closely. So whenever you have a gas at initial pressure and initial temperature, this is proportional to the final pressure and final temperature. So it's a very similar graph to the one I just showed you. Instead, though, when we have an initial pressure and temperature, and if I decide to increase pressure, temperature is going to increase as well. And it's the whole idea of that fast-moving molecule picture. The faster they're moving, if you have a solid container that can't expand, let's say, for example, maybe a gas cylinder, the steel walls, well, if those molecules are heated up, they're going to be really pushing against those walls of that container. So once again, this is a direct relationship, meaning that they go together. As pressure increases, temperature increases. They both increase together. Or the opposite is they both decrease together. Pressure goes down, temperature comes down too. So what kind of problems would you have? So let's say if I gave you the following one. Let's say I had a balloon and I decide to dump liquid nitrogen on it. So if you have a balloon and it's at 3 atmospheres of gas, and it's at room temperature, so about 300 Kelvin, and it's cooled down with liquid nitrogen to a pressure of 0.77 atmospheres. What is the new temperature of the balloon? So if this thing is completely deflated, that's because those molecules are so cold, they're moving really slowly, they're not able to push against the walls of the container because they're not moving as fast. So same as before, we're going to write down all of the key things. So the first one is that the pressure was at 3 atmospheres, and that was at a temperature of 300 K. And notice how I put the decimal place there to tell you that it's 3 sig figs. Now, I mentioned that the pressure changes to P2, and that's at 0.77 atmospheres. So T2 is not known. So we're going to be using our equation, which was P1 over T1 is equal to P2 T2. Okay, so we want to get T2 by itself. Notice how T2 here is in the denominator. So it's really not an easy thing to get by itself. You have to multiply it, then kind of move a bunch of things around. One thing about these equations, if your variable is in the denominator, or the part I have highlighted in purple, what you can do is you can use the inverse of this. So if you have an inverse, what that's doing is it's flipping your whole equation. So if we flip it, well, what's that going to be doing if you flip something? Well, you're just flipping it to be T1, P1 is equal to P2, or sorry, T2 over P2. So if we do that, notice now that T2 is now on the top, meaning that this makes it a little bit easier to cancel out P2 in this case. So now when we try to cancel things, P2 and P2 cancel, and it gets T2 by itself in a really quick manner. It's a good little trick to have in your chemist toolbox to store for later as a mathematical tip. So our formula in this case will be P2, so taking what's over here, P2 T1 over P1 is equal to T2. So when we take all of our numbers from earlier, we'll plug in our new atmospheric pressure. We'll plug in our original temperature, so be 0.77 atmospheres times 300 Kelvin, and that's divided by 3 atmospheres. So when that happens, when we go through that process, what we're going to be getting in a sense is that the temperature of our gas is going to be 77 Kelvin from our mathematics here, which is the temperature of liquid nitrogen when it is poured on something. So 77 Kelvin, that is extremely cold. So that is like roughly about negative 200 degrees Celsius to about or so. It is extremely cold in terms of the most freezing temperature, and then even beyond that. The next law is the combined gas law. The combined gas law takes the previous 3 and puts them all together. So what exactly does that refer to? Well, whenever we have the combined gas law, this is something that it takes Boyles Law, Charles' Law, and Gay-Lussac's Law and puts them all together. So this is something that we're going to go into on the subsequent video of this, to go into how all 3 of these previous laws combine together to make one unique law regarding change of a molecule. So the past 3, all the ones that we're talking about are all about change. Something is increasing, something is decreasing. Combined gas law is going to go into that too. So watch the next video, so that way it breaks up the content for you, so you're not getting a fire hose of information. And I hope that to see you again in the next video to be able to practice more of these gas laws. And we'll go into combined, Avogadro's, and then another video will be on ideal gas law going into that one. Okay? Look forward to seeing you all in the future. All right, bye.